All right, well, welcome everybody to C++ users group here in the Northwest area. So tonight's talk, Remedial C++. So ladies and gentlemen, your boss sent you here tonight because you've been using C++ in an antiquated way. No, seriously, I don't know if you have, but I have. So why have I been using C++ in an antiquated way? Well, because I work on Chromium, okay? So Chrome browser is new, right? Why are you using C++ in an antiquated way on the Chrome browser? Well, because we couldn't use it until all the compilers support it. Well, but GNU supports it, right? Yeah. Microsoft supports it, right? Yeah. But we also have to build for devices like ARM, which didn't support it until quite recently. So in 2017, we were finally able to start using features from C++ 11. Now, one of the cool things about C++ 11 is I got to hear about all the features firsthand from a guy called Herb Sutter, who's presented here before, who should know what he was talking about because he was on the committee helping these features get developed. And I heard about this back in 2007, 2008, when they were calling the language C++ 0x, because they thought it was going to be released sometime in C++ 08 or 09. Well, it finally got released in 11. But that was a good 11 years ago now, and I've forgotten all the wonderful things Herb said. So, okay, let's look backwards. Well, no, it was 8 years when this came out. It was 11 years ago when Herb told me. So with that in mind, let's look backwards at C++ 11 at the new features that have been added. So tonight I'd like to ask you to ask any questions you have right away. If I go through slides too fast, let me know and I can slow down. And with that in mind, let me quickly restart the computer before it goes to sleep. So what are we going to cover tonight? We're going to cover these features. We're going to cover auto for variable declarations, using Lambda functions, null pointer, the default and delete operators to specify that functions should either have the default implementation or no implementation. We'll talk about shared pointer and range-based for loops. We'll talk about uniform initialization. We'll talk about moving objects with the move constructor. We'll talk about the override keyword. We'll talk about the using keyword. We'll talk about constexpr. We'll talk about decal type. We'll talk about the threading library that was added to C++ 11. We'll talk about templates that can take a variable number of arguments. We'll talk about strongly type enums. We'll talk about delegating constructors and the static start function. Sound good? Let's go. So first, auto. So for each one of these, I'm going to try to answer 3 questions. What does the feature do? What's an example? And when's a good time to use it? So auto, what it does is it figures out what type we should use when we're declaring a variable so you don't have to type it out longhand. So here's an example here. You've got a for loop. You basically, instead of having to say the long, convoluted, templated type of this item, you just say auto. You can even specify that you want a reference or a const. And it will declare the proper type of the variable for you. So why does it help? So imagine you have something like this. Okay, you've got a standard vector of network packet called packets. So if you wanted to do a reverse iterator over that, you could just say const auto ref bar, or you could say const reverse iterator open bracket, standard vector open bracket, network packet close bracket, reference bar. You can see the first one is a lot easier to read and takes a lot less typing than the second. So when should you use it? The guidance we have on the Chromium project for when you should use something like this is, first of all, you need to know what type it makes. So you shouldn't be using auto for every single variable so you don't have to think about the type. You still need to think about the type. It's good to know about the type beforehand. And you should use it to make the code easier to read, not just easier to type. As we've already mentioned, it works with const and reference. Okay, next, lambdas. So what are lambdas? Well, it's a way to define a function without giving it a name. Okay, I learned about these long ago in school and couldn't figure out why I would want to use one. But we have them. So here's an example of how you declare one. All this purple code here. So these 2 brackets here are the capture operators, which will capture variables from the local scope to be used inside the function. We have a normal function parameter list and a function body. So in this case, we're making a function with no name and immediately assigning it to a name, which sort of defeats the purpose, but this is just for an example slide. And here's an example of how you might call it. So we could call it with 3 and then a better approximation of pi. Now I talked about how you could capture variables from the scope. This shows how that would work. So we have here a couple of integers, I and j, in the scope. And right here we're going to capture them into the scope. So this means that inside the function, even though we call it later, we can use I and j as they were at the time the function was defined.
Question on the previous
Yes.
slide.
Sure, let's go back. Yes?
When you're assigning to a variable, you pretty much have to use auto in that case? I mean, I think, because the compiler's generating the type, isn't it?
I'm not sure. I would imagine if you knew the type and could express the type, then you wouldn't have to use auto. But sometimes the type is difficult to express.
For example, with that lambda, the type of that is standard function.
It's not. It's actually a closure type, and it is generated by the compiler. So yes, you have to use auto. That's the only way. It has no name that you can express for lambda.
I call it an unutterable type.
Okay? So when would we want to use lambdas? Well, there's a couple situations where they're really useful. Let's say you have some highly asynchronous code. So I write a lot of code this way in the Chromium browser. So we will do something, we'll then need to make some network call. When that comes back, we'll do something else. Depending what that is, we'll make a different network call. When that comes back, we'll need to write something else. So one way to write it is you have a short function which calls something with a callback. And in the callback, you have another short function that calls something with another callback. And then another short function that calls something with another callback. Using lambdas, you can write that in line by putting callbacks as the last parameter. However, you have to be careful. It can make your code difficult to read instead of easier. So when you're doing this, you want to weigh the pros and cons and decide, is this making it easier or harder to read? A second opportunity to use the lambdas is when you're passing comparators or find criteria to some of the standard functions. So if you're using standard find f, passing in a lambda for a comparator might help make your code easier to read than having to have some small function defined that's body is way somewhere else and you've got to go somewhere else to look at it. And Herb had a great presentation here at the Northwest C++ users group back in 2001. We talked all about Lambda in more detail, why it's great, how you might want to use it. The link is right here. So generally after the meeting, we will send out to the email list a link to this video and to the slides. So if you want to go to the slides and the link you get emailed to you after the meeting, you can find it right there. So here's an example of lambdas for a comparator. So here we're using standard sort. So we pass in the beginning of the range, the end of the range, and then this function controls how we're going to determine which comes first in the sort. Here's an example of lambda used for asynchronous completion. In this case, we don't have a big list of them as I talked about earlier, but we just have a fairly simple one. In the Chromium code, bind once basically builds a callback object. So we're passing a callback object into the store initialize, it will get called back, and then we'll do that.
Sorry, once more on the previous slide.
You bet.
You're using the, not sure the technical term, the trailing type syntax.
That's another 2011.
Is that necessary for this particular definition?
I'm sorry, the trailing return type?
The arrow pull.
Oh. In this case, I was lazy and copied this from somewhere else instead of coming up with it myself. I don't think it's necessary. I think there are other ways to declare it that don't require this.
Okay.
I think C++ will infer the Boolean return type in this case.
And I'm not sure that the arrow is even C++ 11. This might have been C++ 14. So I may have cheated with copying this example. My apologies to everybody watching the video and everybody here tonight.
Trish Bright.
Okay, so when should you not use lambdas? So as I mentioned earlier, sometimes lambdas can make code harder to read instead of easier. My personal opinion is that if it needs a function, it probably needs a name. However, I understand there are other programmers who disagree. Here's an example of something that came across my desk. So this is an example in Java. I'm sorry it's kind of hard to read, but you can see what's happening is they're calling a big function here, getPaid by namespace, which passes in a first parameter, and then a callback, which has another function inside of it, which has parameters, and then a callback, which has another function inside of it, which has parameters, and then a callback. As I'm trying to read this code and understand what it does, I basically threw an exception, went back to the developer who sent it to me for code review and said, you know, I think this might be a little bit difficult to read. Maybe we should redo it. And fortunately, the developer did. He did it with only one lambda, which was better.
Just as I say about lambdas for mathematical programming, it's useful to say you're doing some kind of iterative numerical routine, and inside one of the bodies there's some math you have to do. So instead of having that all in one, you know, kind of like what you saw there, you take that out and put it into lambda, and you do give it, like, just call it F, and it's just something specialized for that routine only. So it's not a function that you would use elsewhere. I found that to be very, very useful and makes the code a lot more maintainable.
It kind of allows you to do locally defined functions, which
Yeah, exactly.
C and C++ didn't support.
Exactly.
Okay, null pointer. So this one is pretty simple. It just replaces the venerable null macro that all of us have been using for many, many years now with a typed pointer, null pointer, that points to nothing. But this one is strongly typed, so the compiler knows what it is. So when should we use it? Well, basically all the time. This is one of those things that's just better. There's no good reason not to use it. We recommend using it everywhere. So equals default and equals delete. So these are things you can apply to auto-generated functions to say, yes, I do want one and I want the default, or no, I don't want one, I want you to prevent this one from getting auto-generated. Yes, you have a question?
As I understand, those default and delete are only applicable to the special number functions, the functions that are generated by compiler.
Yes, that's
If
correct.
those are applied to any other function, then we'll get a compile time error.
That's exactly what I would expect. I haven't tried it.
That's actually
Yes.
maybe a bit counterintuitive. These are not exactly symmetrical. So equal, delete, the explicitly defaulted functions, they can only be applied to special number functions. You know, copy constructor, default constructor. Equal delete can be applied to any function. So you can define any function as deleted, which is useful in some, you know, perhaps obscure contexts.
So for example, if the class inherits some function, I can write delete, and that function will not be defined for that class. Is that what you
So
mean?
it is defined. So equal delete defines the function, defines it as deleted. So if you try to call it, the compiler is going to make a diagnostic that you try to call a deleted function. But it is defined. It's not the same thing as not defining it at all.
So you get compiler errors instead of linker errors?
You get exactly. You get better diagnostics. That's the main purpose.
So if you define something as deleted with a specific type, it will override something with a more general type, such as something that could be converted to that type.
You can
But
use it
since
for-
the one with the specific type overrides it, if it's deleted, you get nothing.
you get a diagnostic. So yes, you can use it with
Yeah.
overload resolution is very powerful because you can delete some overloads.
Yeah.
And you can explicitly control. Like if you say you have a function that takes any type, but you don't want to take an integer, you can delete the integer overload, but you can take a floating point. So you prevent, you know, a
Right.
function from defaulting an integer.
Ah, I didn't know that. Good.
Okay, thanks. So here's a couple examples. So let's say you wanted to prevent your class from being copied by having a copy constructor. So you can just delete the copy constructor. Let's say you wanted to use the normal constructor for a class. You could just say equals default. And then you don't have to write it, and you're guaranteed to be using one that the compiler is creating for you. So when should we use these? generally we always use default whenever we want default behavior, and we always use delete whenever we want to make sure that a class is uncopyable. We often, in fact, we usually have a macro that encapsulates the use of delete so that we can just declare this class uncopyable, and it will delete both the assignment operator and the copy constructor. Unique pointer. So you may be wondering, okay, what does this picture have to do with unique? This is from Dale Chihuly's glass garden at Seattle Center. I thought that was pretty unique, so that's how it ties in with subject matter. So what it does, I always have to count and be careful. Resource allocation is initialization, not recording industry of America. So it's a pointer scoping to prevent memory leaks. So we've all probably used smart pointers before, but the base idea of a smart pointer, just in case somebody's watching the video that hasn't heard of them, is to encapsulate some resource within a function so that when a variable goes out of scope, the resource will be automatically freed through all exits to the function.
It'll prevent you from plugging a turntable into your auxiliary input.
Someone would help. So when should we use it? So in Chromium, we use it for all heap allocations. We put all heap allocations into some form of smart pointer, almost always unique pointer. There are a couple exceptions which I'll talk about in a moment. So what's an example of unique pointer? So this is how we can declare a unique pointer. So we'll declare a unique pointer to foo. Standard make unique will call the constructor of foo. In this case, I'm calling the default constructor passing no arguments. We'll have a foo right here at the closed curly brace. When the variable goes out of scope, the destructors get called, foo gets deallocated, and any resources it was holding on to are then properly cleaned up. So here's just another example showing how you might possibly call it, or how you might use it. So you can also declare a variable and then pass in new for it to get constructed. Another interesting idiom is you can have functions that take smart pointers as parameters. You would do this because you want the function to take ownership of the object, and when the function exits, it's responsible for cleaning it up or passing ownership to somewhere else.
May I ask a question about this?
You bet.
What shall happen if we skip std move in the call?
Generally compile error. I skipped SD move a number of times, and it's often a difficult to interpret compile error. So what std move is going to do is it's going to mark this as an R value reference, and the compiler, when it's putting an R value reference into a function, knows that it's actually a move operation. So the compiler will cause the move to happen.
So it's gonna result in an invocation of the move constructor for that purple part. It's gonna be a move constructor, right?
It will be moved. I'm not sure it will be move constructed. So the compiler could, if it desired, from my understanding,
I see.
simply allocate the memory or change the pointers to point to this.
Unique pointers are movable, but they're not common.
So copy constructor for them is disabled and
Yes.
I
It's
see.
deleted. So that's exactly one case where deleted is used. STD unique pointer, the copy constructor is deleted. So if you try to copy it, you get a diagnostic.
Yes.
I'm not hearing a good reason why you should always create a unique pointer that allocated one route to two.
Okay.
Storage up to two.
So what I said is that that's what we do in my code base. So why is it a good idea? Because you want to make sure that at any point in the lifetime, the pointer is owned by something that will make sure it gets deleted no matter what happens. In C++, exceptions can be thrown in a huge number of places. Even a humble plus sign could end up throwing an exception because if the plus operator is overridden, something happens. So what we generally do to keep memory protected and make sure that the resource is released is as soon as any resource is required, it's put in some kind of resource protection. Now this is something that we do in our code base as a matter of we think it's a good idea. Do you need to do that in your code base? No, but we recommend it.
But as, say, some other type of shared pointer.
Well, we're going to talk about shared pointers in just a minute.
Right. But why, well, I just want to know why if you're allocating off the two, you want a unique pointer rather than some other type of managed
Okay. You want some kind of managed pointer. In most cases, I think unique pointer is the right thing to use because shared pointer is a little bit more difficult to use. We'll get into that in just a minute.
Also less efficient.
Yes.
Yeah, unique pointer is, I think, essentially a no-cost abstraction. Or close to it.
It's definitely
Shared-
a low-cost
shared-
abstraction.
Yeah, whereas shared pointer, there'll be a cost, kind of like on the order of Java or Firefox.
Right, the shared
That's
pointer
why
would
I
have to
understand.
maintain some kind of reference count, at the very least.
Having exactly one owner is easier to reason about in some
Yeah.
cases.
Yes. You've been reading 4 slides ahead, I see.
pointer.
No, I just do this every day, you know?
But it scares me if I call a function and give it a unique pointer, then it disappears in that function.
Okay,
I
so-
can't use it when I.
Right. So whether you want a unique pointer or a bulk pointer to go into a function is a matter of how you want to manage your lifetime ownership. So just because I said here we can call a function with a unique pointer doesn't mean that that's the right thing to do. If you want the outer scope to stay in control of the lifetime of the object, then you'll often use get, you'll pass in a bulk pointer, and you'll have a coding standard that says, if I pass in a bulk pointer, I may not delete it. It's owned by somebody else. Does that answer your question?
Yes.
All right, let's move forward. All right, now shared pointers. So what is a shared pointer? It's basically a smart pointer that's reference counted. So I can give out one copy here, and one copy there, and one copy in the other place. And the resource it's protecting doesn't get cleaned up until all 3 places are done with it, which is good as long as all 3 eventually finish. So let's do a couple of examples of shared pointers found in actual code. So in this case, we have a shared pointer to the job object. And the shared pointer isn't actually being used, it's just used to keep the job object alive while doing this asynchronous step until we come back and can finish. Here's an example of how a shared pointer might be declared. It's just a standard shared pointer of brackets, whatever type it is you're interested in sharing. Here's an example of some accessors that take shared pointers. So in this case, we can set the storage for the wire bytes and get the storage for the wire bytes. So one interesting thing to notice here, it's sort of hard to see the green on the black, is we have a mutex guard. So anytime you're seeing shared pointers, one of the reasons you might want to use them is you have multiple threads accessing something, which means you're going to see mutexes in a lot of the places where you see your shared pointers. Okay, here's another example of a use of a shared pointer. So we just see here where a shared pointer is being passed into a function. And we see here one of the calls to the accessor we just looked at. And in case you're curious about the class we were pointing at, that we have a shared pointer to, this is just the class we were pointing at. Yes, you bet. Do we need to go back further, or was this enough?
And the pointer. Oh, okay, go ahead. Yeah.
Okay, on we go. So when should we use a shared pointer? So we try to avoid it in our code base whenever possible because it's easier to reason about unique pointers, just like Chris was saying earlier. So with a shared pointer, you end up handing it out in a bunch of places, and it's hard to know if all those places have finished with it, or if somebody has tried to call free a couple of times. These are really difficult issues to debug. So there are times when you need it, but generally it's a lot easier to use a unique pointer if you can get away with the unique pointer. As we mentioned earlier, one thing you might use it for is multi-threading. So when you're doing multi-threading, you may want an object that's given out to several different threads, and you might use a shared pointer to keep them all alive. Okay, next, range-based for loops. So we saw an example of this before when we were talking about auto, but basically it's an easier to read syntax for loops. Java's had this for ages. JavaScript has had this for ages. Isn't it about time C++ got it? Fortunately for us, C++ finally did. So the syntax is really simple. So instead of for, you've got your initializer, you've got your condition, you've got your increment. We just say each item in a container. And we can even use auto to make it easier to declare the type of the item. And then inside these brackets here, the variable item will have a reference to or a copy of whatever thing you're working with. You can do your work, and it's that easy. This is another one of those things that's just good, and we recommend using pretty much all the time. Okay, uniform initialization. So what it does is a way to initialize objects. Okay, well that was kind of obvious from the name. Let's go into a little bit more detail. So why do we need uniform initialization in the first place? Before we had uniform initialization, C++ was kind of inconsistent when you were trying to initialize things. So if you wanted to initialize a string, you could initialize it just like this, with the syntax that we now use for uniform initialization. But what if you wanted to initialize a vector of strings? Oh no, that doesn't quite work. It did work with the array of strings, but not with a vector. What if you wanted to pass it in to a function? Oh no, that doesn't work either. So with uniform initialization, all of these different ways of doing the same kind of thing work hopefully the way you would expect them to. So if we have an integer array, we can just declare the elements in line. If we have an array whose length we don't actually even have to specify here, we can just declare those elements in line. We can do a vector the same way. We can do a set the same way. If we want to do something more complicated like a map, we can initialize the map there. If we want to pass in a vector as an argument to a function, we can pass in a vector as an argument to a function. Yes?
For the line 2, we don't have to specify the equals sign?
I believe the answer is no. So we'll see that on my next slide. So these are several different syntaxes you can use with uniform initialization. So first one, we're referring to X up here. You'll notice that I didn't call a constructor to X passing it in variables. We can just use the initializer list itself. And here, we could do it with an equals or without an equals, and both will work equally well. Here's another example of calling new as if it were a constructor. Here's an example of passing values to a base class. Here's another example of passing values to a base class.
And you can do this for types other than aggregate types. Yes?
Yes, you can do this for any
You
type.
can do this
as
for
long as,
integers and...
right, as long as the compiler can figure out at least what it is you want to make the arguments match, you can do it. So, when is it good to use? Lots of times, it's good with array elements. It's good with objects where it makes sense. Sometimes a constructor may make more sense. When should you not use it? There are a few cases where it doesn't do exactly what you'd expect. So we can get into a case where a template may not know whether a number in a uniform initialization is a value or a number of elements. How could that happen? Well, I'm glad you asked. We have an example right here. So let's say we have a template. It'll take some type T that's supposed to create 10 elements, and then we'll just return a standard vector initializing with 10. But depending on what the type T is, you might get different results. So if you pass in a standard string, 10 elements, we're good. If you pass in an int, you get one element with a value of 10. Ooh, probably not what I intended. If you pass in a widget, it creates one element for some widget definitions if they have a constructor that takes a single integer, and 10 for others if they don't have that kind of constructor. Char creates one element with a value of, what is 10? Line feet, I think. And then this one here actually creates 10 elements. So on the Chromium code base, our Google style guideline allows it. It does give us a warning that we should be careful when using a braced initialization list on a type with a standard initializer constructor. So there's two caveats for uniform initialization. Other than that, though, it appears to be a pretty good thing and work well.
I would say 3.
Okay, what's the third caveat?
Using auto. If you use auto and assign, and you will get, in C++ 11, this has been corrected, but you will get a type initializer list.
Okay?
rather than what you might have hoped for, like an array of integers or something.
Yep, you're right, and thanks for bringing that up, I missed that case. There's one good thing that the uniform initialization can do for us. So without uniform initialization, if you try to call int pi passing 3.14, the 3.14 gets narrowed to an integer type, and it succeeds, which is probably not what you intended. However, if you do it with uniform initialization syntax, you get a compile error. It knows that you're trying to do a narrowing conversion. It says that probably wasn't what you intended. Okay, moving instead of copying. So we talked a little bit about this here with R-value references and moving pointers, but we'll go into a little bit more detail. What this does is it allows you to prevent copying as you move up and down the various layers of calls. My favorite example here is the Windows networking stack. So the Windows networking stack, when Windows XP came out, I think it was XP SP1, they had the new TCP/IP stack, gained huge performance wins by just not copying things. They would write the data into memory once, and then would pass through all the layers of software, through the NDIS driver, up to the TCP driver, up to the application code, without having to copy it at all. So they only had to write things once. We can do the same thing in our code. I find a lot of my code is layer calling layer calling layer, and if I can pass something in or move it instead of copying it, I end up with much more performant code. So here's an example. We've got some punch data routine. I can just pass my data in with a standard move like we looked at before. When is it a good idea to use this? In our code base, we use this as much as possible. Wherever we can, we try to move data instead of copying. I like this topic so much, I even did a presentation on it right here at Northwest C++ Users Group, which some of you will remember, but others may not have been here that night. And here's a link to the presentation right here in case you want to watch it. Okay, next is override. So what does override do? Override just makes explicit that we really want to override a virtual function when we're writing a derived class. So here's an example of how to use it. So let's say we have a virtual class called task, which has a run function, and a derived task, and a derived test task function. We put the keyword override after run, which will basically throw compiler errors for us if it's not actually overwriting something like we expected it to. So let's say run had a parameter list with 4 parameters, and we declared it with 4 parameters here and 3 parameters here, thinking we were overriding the function. But we wouldn't be. We might silently get an error otherwise. But once we have the override keyword, we will get an error. So when is it a good idea to use the override keyword? We try to use it all the time in our code base. We think it's a good idea. All right, const expr. So what const expr does is it basically tells the compiler that this thing is a compile time constant. You can go ahead and compile it, compile time, make it a constant so we can use it. It also implies constant. Here's a couple of examples I found from the code base. So in the first case, we're declaring a constant, which is based on some other things we have to calculate that are known at compile time. In the second case, we're actually declaring a constant function. So when should it be used? We use const expr a little bit more sparingly, so we will use it when it makes sense, but it doesn't always make sense. The guidelines from our coding standards are you shouldn't try to make things more complicated just so you can use const expr. But if it does make sense, it's fine to use it. Oh, and also don't use it to force inline. You bet.
Excuse me.
You wanted to ask a question first? And I'll get
Oh,
to
I'm
that.
sorry, I didn't know there was, oh.
Go ahead.
So, what's the difference, what you're saying? Well, you wouldn't say static const, but if you just had like a const size t, it would not be basically the same thing.
So I think the difference is this equal sign here. So we know that there's going to be a constant variable of size t. But this thing here, we want to make sure the compiler knows gets computed at compile time.
But I think it normally would be computed, that would be computed at compile time. Because you could even use that as size of an array
Yeah.
compiled.
Mhm.
So
Could be
what
computed
does
at compile
const
time.
expression by you?
Yeah, it could be computed at compile time. I'm not sure that every compiler does that. And I could be wrong here. At this point, I'm guessing.
Language doesn't guarantee that just const can be used at compile time. For example, in an array size. If it's const expert, then it can. But const cannot, in general, in the language definition, be used as an array size at compile time. For
Although
example.
probably most compilers will do it. But there's not a guarantee that all compilers will.
Not in the official language.
Okay, this is something I've used all the time. Haven't gotten into trouble.
You're lucky.
So the optimizer, it wasn't doing this all along?
I think it might depend on your compiler. I think many of the good compilers we use every day are. I'm not sure that every compiler does. So for Chrome, we have to compile things for ARMs. We use all sorts of different compilers. Dan, do you have a question?
Yeah, when I've read about the new features and CPP Conno, they say, yeah, they're really high on const expert. Just use it, it kind of strive to use it almost like by default. And again, in mathematical coding, I'm hard pressed to find a real compelling reason to use it, because it's going to be great for if you have something integer valued, which you can then put in at compile time. But if your computations are all floating types, then I just don't see any advantage. Can you point out?
So I'm
I
guessing
mean-
the advantage that they're thinking of when they tell you when to use const expert as much as you can is every piece of data you make const makes the compiler's job just a little bit easier and can help in theory make your code just a little bit faster. Does that help?
Still not. Well, maybe we can take it offline.
Sure, yeah, we can talk about it afterwards. I'm happy to do that.
Does const expression allocate storage for the variable? Or is
It
it
shouldn't
purely
need to.
compile time?
It shouldn't need to. It should be able to just turn it into a constant compile time. Walter?
One thing you can do with const expression and floating point is if you have like a table of signs, a fast lookup table, you
Okay,
can initialize the table at compile
Gotcha.
time.
Okay, so that would work. Okay.
Well, I don't know if it'd work in C++, but that's what I use. That's what we use const expression for.
Okay, that would make sense.
Yeah, it uses an awful lot to initialize tables that have
Okay,
a non-trivial computation to them.
Gotcha. Okay, yeah, that makes
And
sense.
it works really nice for that.
Okay, cool. Thanks.
Okay, any more questions before we move on? All right. So using. What does using do? Well, it's a lot like typedef. It just sets up an alias for a more complicated name. So here's an example of using. I like saying that. So we have using data point, which is just going to be an alias for a pointer to the bar that's inside foo. We're using time series, which is going to be an alias for this large, hard to write, standard unordered set of data point, standard hash of data point, and data point comparator. So when to use it? So one of the things that is in our coding standard that we should not do is we should not do using standard and bring in the entire standard namespace. But it's okay to use with standard string. So if you want to bring in just one class with using with something simpler, that's good. Now, since you may notice I've described using exactly like typedef. It basically is an alias for another name. So when should you use using and when should you use typedef? So the rules that we have in our code base is that using is preferable to typedef because it's going to give you a slightly more consistent syntax with the rest of C++, and it works slightly better with templates. Now, everything beyond this in the lecture is something I have not actually used yet. So all the things before I've used at least once. I've seen them in our code base. I know how to use them. For everything else, I've tried to go to the web and go to our coding standards and bring you the best wisdom I can, but it's not personally based wisdom. So we'll do the best we can. Bear with me, and off we go. So decal type. What is decal type? Why would you use it? Is it declaring a type? Well, it's actually an expression that's going to return the type of the argument. So kind of like size of returns the size of the argument, decal type will return the type of the argument, and this is a compile time object. So when you need a type of something, decal type can help. All right, so what are some examples of when you might want to use it? So it's good with type def and using. If you've got a thing whose type might be hard to say, but you know the thing, you might be able to take its type and then say, okay, every time I mean the init proc now, it's going to be the type of the reference to nvml init. So in this case, we're using a function to unwrap something to get a type out of it, and unwrap will be the type of the thing that we wrapped up. Yes, Robin?
In that first decal type case, nvml is a variable,
Yes.
and ampersand returns a pointer.
Yes.
So decal type defines as a pointer type.
Right, so it'll be a pointer to that variable. So in this particular case, we're using get proc address to get the address out of the DLL.
Okay, thank you.
Okay, here's another example of a template that's using decal type to get the type that's inside the list.
I'm sorry, can we go back one?
You bet.
For the unwrap,
Yes.
that's a function, is it not?
Yes.
Okay, so unwrapped is a function type.
No, it's
Or is it the
Result of the
return
function.
value?
Yes.
It's the type of the return value.
I
Ah,
believe that's correct.
okay, sorry. I didn't notice the call.
So when is it a good idea to use decal type? Sometimes when you're writing a template, you need to know the type of something, and for one reason or other, you might not be able to use the key that was a template parameter. So when would that happen? Oops, I don't have an example, sorry.
Well,
As I mentioned, these are things I haven't actually used. Chris?
yeah, in pre-C++ 14 world, you use decal type to make lambdas with types that you didn't necessarily know what the return type is. But now you can just use auto. So if you're in a code base that's only C++ 11 and down, then you use decal type to make those kind of lambdas. Otherwise, you can just use auto now. But that was my usage of decal type.
Awesome, thank you.
How is that different than type ID?
So type ID returns it's a runtime value that it returns. It's actually a value that you can pass around. Decal type, it's a compile type. It's names a type. You can use it to declare a variable or have a ADS.
Okay.
So you can use decal type in a return type for lambda. Unlike you could use type ID to do that.
Okay, let's move on. The thread support library. So there are a bunch of libraries that were added in C++ 11, new capabilities for every programmer to use. There are so many that I'm not going to have time to talk about all of them tonight, but I'm going to talk about one of them, the thread support library. So what does the thread support library does, or what does it do? It gives you the things that you need to write multi-threaded programs. Now in our case, we had already had the things to write multi-threaded programs for many years by the time this came along. We ended up not using it. It has some benefits that will make things more portable, but many of you may find you're working in a code base that already has libraries that will do all your threading work for you. So it will include things like a thread class, mutexes, futures, and so forth. So let's do a quick example. So at the top here, we have a function, call from thread, which will get called from a new thread. We create a thread object using standard thread with an argument of the function we want to get called. This will start a thread. It will cause the thread to get called. And then when we want to wait for it, we join so that the main routine will not proceed until the thread is done. And then we're done. So as I already mentioned, we don't use it. When I was looking for reasons why one might want to use it, I read that it's a little bit more simple than POSIX, and it can be portable if you're going to be compiling for multiple platforms. In our case, it would be important because we compile Chrome for all sorts of things, but as I said, we already have our own library.
So, in Chromium code base, you don't use the newer functionality because the older functionality exists.
Yeah, we're not using older functionality of C++, we're using older library that we already had. So we built many libraries when we were building Chrome. One of them was a threading library. We basically used that instead because it's sprinkled throughout the whole code base. And a huge amount of code was written before we were able to use C++ 11.
So even for a brand new code that is relatively autonomous, you still don't use the newer thread library?
Well, we don't have any new code that's autonomous in Chrome. It all fits together in one big binary. If the Chrome team were to start a new project, there's a good chance we'd use this.
Should we write your threading library to use the C++?
We certainly could do so. I don't know if there would be some kind of abstraction mismatch or interface mismatch if we tried to do so. Yeah.
In what you have already, do you have task-based multi-threading like the C++ 11
Right, generally we
standard?
have a series of task queues and we post events to the task queues. Unless we're doing inter-process communication, which happens through a different method.
Okay, so you already have that
Right, we
type
already
of
have
functionality in there, okay.
a ton of functionality in there. There's
Interesting.
more than the thread class does for us.
Like TBP, which is based on whatever threading library is available on the platform, but the TBP abstracts that to a portable.
Exactly. So we've got something that abstracts out the work on Mac, Windows, Linux, Android, anywhere else we like.
So the C++ one is mutex based then?
The threading library we use,
No, the C++.
the C++ one. They have their own mutex objects that are part of the standard threading library.
Because Windows has something called section, which
Yes, Windows has lots of different synchronization primitives.
is far more efficient when you use it.
Something else that C++ 11 brought to us is some new containers, like the unordered containers. So what they do, they're sort of like a hash map before C++ 11, but you can make some where order isn't important. So before it brings you is unordered map, unordered set, unordered multi-map, and unordered multi-set. Here's an example of how you might use an unordered set. So we'll make a set of strings. We'll add first, second, and third to the set in that order. After we've done that, if we add a second time, then it doesn't make any change because second's already in the set. And then if we decide to display everything, they won't necessarily come out in the same order we put them in, or in alphabetical order, or in any specific order. So when to use unordered? Basically whenever it meets the time complexity requirements that you have for your application. Okay, this is one of my favorite additions, is variadic templates. So what's a variadic template? We know what printf is, right? It takes any number of arguments. How about a template that takes any number of arguments? Well, gee, why would you want that? Well, if you've ever seen the Loki library that Andre, who used to come here from time to time, wrote, he had to have, for type lists, a whole bunch of different definitions of every template. One for one argument, one for two arguments, one for three arguments, one for four arguments. And of course, it's not here, but it went down to about 10. That would certainly be a case where being able to have a variable number of template arguments might help. So here's an example of how you can use it. So in this case, we're passing the type name ... and the ... here. And it basically works to be able to, in this case, it's going to unroll at compile time and add up everything. But you could apply it to other things too. So when should you use it? Well, whenever your use case calls for it. I don't have any better advice for you than that. Okay, last one. It's been a long evening already, so thank you for staying with me this far. Strongly typed enums. So this one is pretty obvious from the name. So the old way of doing enums is you just say enum selection, you have an enumeration, you assign it, you're done. But what you get isn't a type of enum, you get a type of int. And you might not even know whether it's a 8-bit int, a 16-bit int, 32-bit int, 64-bit int. With the new enums, you add the word class there, and you'll have to qualify it when you're using it. But at this point, it will enforce that whatever goes into selection is actually going to be a member of this enumerated class. When to use it? Well, it always helps to have more type safety. and helps they don't get converted to int automatically, so we definitely use them in Chromium. And also, a new feature that comes in with C++ 11 is you can, when you're defining the enum, tell it what type you want it to use underlined. So if you always know it's going to be a very small type, you might want to assign char. If you know it might be a very long type, you might want to use the 64-bit int. I'm sorry, I thought it was last. I forgot about delegated instructors. So this basically lets one constructor call another constructor to do its work. So for example, if we have constructor A that sets 3 variables, then the delegated constructor, which takes 1 argument, can use constructor A to set the 3 variables, and they can override just the one that it wants to. When to use it? Basically, whenever it would save you some work, if there's some boilerplate section of things that needs to be done for all the classes, you can do the boilerplate in one place and just do fix up everywhere else. Okay, static cert, all right. I'm sorry, I thought that was the last one. Maybe I got messed up between the S and static or static cert and the S and the strongly typed enums. So what this does is compile time asserts. So basically you can have your program break at compile time so you can detect earlier on that you've got a problem. The problem, bad code never even gets compiled. Here's an example we use from our bind class. So remember we talked about the base bind earlier, which creates callback closure objects. In this case, we want to make sure that the closure object is a type that's forwardable and a type that can be constructible, and we want to give you this error message if it is not. Very helpful deep inside libraries to make sure that we're properly using the right assumptions and communicate to the programmer what might go wrong when you're trying to use that library. Okay, that's the end of all the features I'm going to cover, but I do have a few more slides. So there's lots of new library additions I didn't cover, as I mentioned earlier. So these are some of them. So there's standard move, which we talked about, forward, thread, which we talked about, toString, which we didn't, tie, which we didn't, read pointer, which we didn't. As you can see, fairly big list of things. A few links, so if you wanted to look at some of this information on your own, these are some of the websites that I found that would try to teach poor old programmers who didn't know how to use C++ 11 yet, how to upgrade to C++ 11. So there's these two here. There's a complete list of all the features of C++ 11 at this site. And if you want features from C++ 14 and C++ 17, this site will have those too. There's an official C++ 11 website to look up everything. And I mentioned the Chromium style guidelines a number of times. If you want to look at those for any reason, they're right here. And lastly, a reference to C++. That's all. Thank you everybody for listening. If you want me to see me try this again for C++ 14 or C++ 17, or go through the library edition of C++ 11, let me know and I'll have one put me on the schedule sometime in the future. If this was really boring and you don't want to see this again, don't let anybody know. All right, thanks everybody.